Okay, today I thought maybe we would look at some other sort of more interesting configurations of engines, and then of course we'll get to some of the most advanced means of propulsion, getting into jet engines and that sort of thing. So very quickly, we'll just have a quick look at the Wankel. The Wankel rotary engine, some of you may know, was used in the Mazda RX-7. So that was a production car that actually used this kind of engine, sometimes referred to as a Rotax. And the thing that's different about this engine is that rather than using a piston that goes up and down, we're using this kind of interesting triangular shaped piece in the center here, and an oval shaped combustion chamber. And the advantage to this is that we don't waste any of the engine's power in trying to convert from up and down motion to round and round motion. So we've got we're instantly creating circular motion. So if we wanted to drive the wheels of a car or the transmission of a car, that can be done very simply without having to move the pistons from the up and down motion into rotational motion. So that's the Wankel. And if we stop this, I'll just kind of give you a look at what's happening here. You can see here's our intake valve here, or our intake port. There is no valve on it as such. And as this shape sort of rotates around inside this, it creates a low pressure zone, which would pull in or suck in this fuel and air mixture. And if you watch, you can see that that space gets bigger and bigger and bigger, so it would suck in more and more and more. And then all of a sudden it starts to compress. You can see that the fuel particles are being compressed a little bit here as this rotates down. So the compression is happening at this point. And you can see we've got these little cutaways here. This is so that there is actually some space for the fuel-air mixture to be able to go to when this completely bottoms out at the bottom here. So you can see all of that fuel-air mixture gets compressed into this tiny little space, and then we have ignition happening over here, which starts to push that device around, and we have our flame front rolling out, and then of course the exhaust, if you want to call it a stroke, but the exhaust portion of the process is happening up here. So that's the Wankel rotary engine. Very interesting engine, and there's certainly more that you can find out about it down there if you'd like. You should ask Mr. Panisi when we get back to school. He actually has a cutaway of this engine in his shop. So now let's move on to jet engines. These are very different because first of all, we need to make a distinction between rockets and jets. But before we do that, we should understand that what we've done with these sorts of engines is that we are no longer trying to contain the expanding gases and use them to move a piston as such. We know that from Newton's laws of motion that every action has an equal and opposite reaction. And so if we have gases that are expanding out the back of an engine like this, then that means that the engine must be responding to those expanding gases by moving in the opposite direction. And we get something called thrust as a result of that. So if we're ejecting a whole lot of stuff out the back, that eventually will cause this to accelerate in the forwards direction. And that's how thrust works. And this is how we make airplanes fly. It's how rockets go up into space. It's what SpaceX does, and Virgin Galactic, and all of those sorts of things. So a rocket engine basically relies on two different things: an oxidizer and a fuel source. In a lot of rockets, this would be sort of kerosene and maybe liquid oxygen. And we mix those together in a nozzle and then ignite them. And when they ignite, they basically, the flame never goes out. It's not like we've got an intake stroke and then a compression stroke. We're simply mixing those things continuously, and the flame and the exhaust gases simply spew out the back of the engine in a continuous fashion, creating continuous thrust in the forward direction. This can be done with liquid fuels, but it can also be done with solid fuels. So some of you might remember the space shuttle, the two smaller rockets that were on the sides of the space shuttle were called the solid rocket fuel boosters. And so those would have been more like, you could think of it almost like a firework arrangement where we're not using liquid fuel. And then the main thrust body was, I believe, liquid hydrogen or liquid oxygen, which is pretty clean burning and efficient. So that is the way that basically these engines will work. And we use rocket engines because we have to take them out into space. And in space, of course, there's no air. And so there's nothing to oxidize the fuel in. So we have to bring our own oxidizer, this oxygen, liquid oxygen, or something like that that would allow for combustion to occur. If we're staying at least in the Earth's atmosphere, we don't have to bring along that oxidizer because we can take for granted that there's oxygen in the air. And that's where ideas like the turbojet and the turboprop and the turbofan come in to play. And these are all different takes on the same idea. But I'm going to I'll go through how this works. And then I will post a video for you to watch if you're interested, only if you're interested, which takes you through a cutaway of one of these turboprop. It's a turboprop engine, I believe, that they are looking at. And these are used not only for driving propellers, but they can also be used as a power source for lots of other equipment in industrial processes. So they're not just restricted to aircraft. They're also used in industry for a variety of things. And in fact, an engine very much like this is what powers some of the most advanced tanks in the world. You'd be surprised, I think, to think about that. But we are actually using the turboprop engine to power tanks, which is kind of interesting. So again, we've got this idea. Up here, we were talking about thrust. And here, we've got the same thing. We have thrust exiting out the back of the engine. But the interesting thing is how this all works, because it's a little bit more complex than people might imagine. Up here, you can see these two things here are called compressor blades. And these compressor blades, basically, depending on the engine, there may be 2, 4, even 10 rows of these compressor blades. And then in between the compressor blades, there will be something called a stator. That's what these things here are. And the stator basically realigns the airflow after compression has happened and makes it ready for the next stage of compression. And this becomes really important because what we do when we do this is we compress the amount of air, so we're increasing the amount of air that's available inside the combustion chamber. And that means that if we increase the amount of air, then we can increase the amount of fuel. And if we have fuel and air burning at an increasing rate, then we get increasing thrust. Now, in order to make this sort of self-sustaining, what the engineers have done is they then put these turbine blades, which are almost the reverse of the compressor blades. The turbine blades are at the back, and they would have a stator in between each set of turbine blades. And as these gases go through the turbine blades at the back, they cause this shaft running up the middle to rotate even faster, which causes the compressor blades at the front to compress more air and fill this combustion chamber with more air, which means we can now add more fuel, and we get a hotter flame and higher temperatures and higher expansion of gases, which in turn feeds the turbine at the back, which keeps the fan blades spinning at the front, and so on and so forth. And then, of course, the exhaust gases are exhausted out the back, and we have Newton's laws of motion, which basically mean that this pushes forward. If you put 4 of these on an aircraft, you can actually lift, a very, very heavy machine full of people and luggage and everything else into the sky. So it does actually work, despite the fact that it seems very simple. If you look down here, we could do the same thing where we actually introduce a gearbox and we drive a propeller. So Propeller-driven aircraft could use this kind of a turbo prop or turbofan arrangement. And again, you see here at the back, we've got even more of these turbine blades at the back, and we've got lots of compressor blades at the front. But basically, it works the same way. We just have a gear that reduces the speed of this engine so that it can actually power a propeller, which is what drives most of the thrust. So here, we're not talking about getting thrust out the back of the engine. We're trying to use that thrust to drive these turbine blades here, which in turn spins the shaft at the front and drives the propeller. And the propeller is what provides the thrust. It's like turning an airplane wing horizontally and having it slice through the air to create that forwards motion. And it's this configuration here that's used in industrial applications. If you can turn a propeller blade like this, you can imagine we could hook up pretty much anything that we want to this, whether it was a pump or we might be trying to power a compressor for compressed natural gas in pipelines and things like that. In fact, this is one of the major applications of this engine is in pressurizing pipelines. And the thing that's really interesting about it is that we can use a variety of different fuel sources for this too. So it doesn't have to necessarily be configured to use aviation fuel or kerosene. It can also use natural gas. So if you're in the business of providing pressurized natural gas and you have lots of that around anyway, you can use some of it to drive a turboprop like this or a turbine engine to help pressurize the pipelines themselves. So that's another way of looking at it. And then, of course, there's the turbofan, and the turbofan then has these this fan blades out in the front, and that creates this flow of air through here, and we get thrust out the back of the engine in the same sort of way, but not so much coming out the back, not where you're going to have an afterburner or a flame coming out the back of the engine. And these are the main engines that would be used in aviation. You might ask yourself, well, why do it this way as opposed to with a propeller or as opposed to with just a simple jet? Well, it depends on what the application is. For lower altitude flight, we typically want to use propellers because the air density is better suited to using a propeller. For higher level flight, where we're worried about long distances and better fuel efficiency, we probably either want to use a turbofan or perhaps even the turbojet, because that allows us then, with thinner air and a compression system, we can compress that thinner air and get a better fuel burn inside the combustion chamber. And that's how that works. So, hope you enjoyed it today, and I'll leave it there for right now.